Hello and welcome to the presentation related to the topic of dimensional analysis. This is actually a continuation of the presentation related to dimensions. The previous presentation outlined the use of dimensional homogeneity to solve various problems involving the dimensions MLT theta. The presentation now considers some further problems in which we're going to find unknown exponents from given formulae and equations. So for example, we might be given the formula I is equal to bd to the power of x divided by 12, and we're going to show how to use dimensional homogeneity to find the numerical value of x. It is assumed you've seen the previous initial presentation related to the use of dimensions before reviewing this presentation. Very briefly, we outlined some recap slides from the initial presentation on dimensions. Here are the SI base units, length, mass and time, showing the dimensions of L, M and T. Those are the predominant dimensions we'll be using within the problems. And here's a recap slide of exercise 1 from the initial presentation, listing SI derived units. So for a given quantity, we have the symbol, the SI unit and the dimension. This table was used as a reference source for solving various problems in the previous presentation. This slide shows the first part of table 2. Here's table 2 continued. Further quantities, units and dimensions. The final part of table 2, again showing further derived units. The recap slide here, highlighting the main dimensions we'll be using of mass, length, time and theta for temperature. And also to note that the laws and the rules of indices are very often required when solving these dimensional type of problems. In particular, the third law of indices shown here, raising a power to a power, and the reciprocal rule of indices shown here. It's also useful to note that anything to the power of 0, of course, has the value of 1 unity. So there are 4 problems that will be worked through in detail. Here's problem 1 and problem 2. Answers shown in the brackets on the right hand side here. Having reviewed the initial presentation, you may feel you can attempt these questions without further assistance. If that's the case, I would encourage you to stop the presentation and do so now. But the full work solutions will be shown later in the presentation. And here are problems 3 and 4. Again, answers stated in brackets on the right hand side. And here are the approximate start times related to problem 1 through to problem 4, should you want to jump directly to the commencement of these problems within the presentation. Please note though, these times are rounded to the nearest minute. So let's outline problem 1. For a rectangular section in bending, the second moment of area, symbol I, having a unit of meter to the power of 4, is calculated from the formula I is equal to bd to the power of x divided by 12, where b and d are the width and depth respectively, and both are measured in meters. Using dimensional analysis, we've got to find the value of the exponent, power if you like, x, in the above formula, and thus we've got to state the final equation. The answer is shown here. Obviously it shows that the exponent in this case is 3. So if you can attempt this question without further assistance, I would encourage you to stop the presentation and do so. But the full work solution is shown on the following slides. So problem 1, we're given in the question, I is equal to bd raised to the power of x divided by 12. So the first thing I do in these questions is to note the quantity. Secondary moment is I, SI unit is meter to the 4. So in terms of dimensions, that will be L to the power of 4. Notice again I use square brackets to denote dimensions. We're informed in the question that width B has the unit of the meter, so dimension will be L, and depth D, meter L. So assuming dimensional homogeneity, we can now replace the I on the left hand side of the formula given with the dimension L to the 4, L to the power 4. On the right hand side we can replace the width B with L, and I put to the power 1 there. The default is 1 of course, and D is L to the power of X. So that's the formula stated in terms of dimensions. Notice as always the constant 12 is not required within the dimensional analysis. Constants are ignored from the solutions. So problem 1, solution continued here, just repeated the top line for convenience. So now we're going to use the process of equating indices between the left and right hand side of the equation for lengths L. So don't forget we're equating the indices here. So on the left hand side we have L to the power of 4, so there's my 4 on the left hand side of my equation. On the right hand side we have L to the power of 1, so 1 on the right hand side, and L to the power of X. So my equation generated by equated indices is 4 is equal to 1 plus X. Subtracting 1 from both sides, then 3 is equal to X. So we can now state our formula as I is equal to BD cubed divided by 12. And that's a standard formula you'll find in any text or reference books related to the second moment of area of a rectangular section in bending. And purely for reference, here's an extract from our beams in bending presentation calculating the second moment of area I value about the neutral axis. Here is problem 2. We're asked to determine the value of the unknown powers labelled A and B. In the equation for work done, capital W here, work done is considered to be a function of mass density rho, volume and height h. We're given the SI unit for work, it's the joule. For mass density, it's kilograms per meter cubed. For linear velocity, it's a meter per second. And for height h, the unit is the meter. The answer is shown in the bracket here for your reference. If you want to attempt problem 2, please stop the presentation, do so now, but the full work solution is shown on the following slides. Here's problem 2, beginning of the solution. We're given the question that work is considered to be a function of mass density, velocity, height. As always, we will assume dimensional homogeneity. So if we now insert the SI units for the various quantities, work on the left hand side, and that's the joule, which of course is a Newton meter. Mass density is the kilogram per meter cubed. Velocity is the meter per second. Notice that's raised to power A, of course. And the height h as a unit of the meter raised to power B here. Well, next line I simply insert the dimensions. We know from our previous lecture that the Newton can be written as mLt to the negative 2. Referring back to our table 2, force is the unit of the Newton, but don't forget a Newton is actually a kilogram meter per second squared. It's a derived unit of course, and that has the dimensions mLt to the negative 2. That's what's shown here, mLt to the negative 2. And of course the meter is actually dimension L. On the right hand side the kilogram is mass, so that's m, and it's kilogram per meter cubed. So I can write the m as dimension L, and I'm going to use a negative rule of indices here, reciprocal rule, so I can write that as L to the negative 3. And again, referring back to table 2, the mass density, mass divided by volume, SI unit, kilogram per meter cubed, or kilogram meters negative 3, and that has a dimension of ml, negative 3. And again, that's an extract from the initial presentation on dimensions. The meter per second, meter has the dimension L, and per second here, second has a dimension of t, so again I'll write that as t to the negative 1, and the unit of the variable h, height, is the meters, so that has the dimension L. Again, notice the exponents or the powers are still included here. On the next line, I've simplified the left-hand side. I've multiplied the two L dimensions together to produce L squared. On the right-hand side, I did just simply add this 1 power exponent to the L. We don't normally write the ones. We assume a 1 if nothing is stated. But just for clarity, I've added the 1 here. And the final line of this slide, I've divided both sides by m, so the m will cancel on the left with m on the right-hand side. And just note that I've used the third law of indices here to raise the terms in the velocity bracket here. So L to the power of 1 raised to the power of a becomes L to the a. And t to the power of negative 1 raised to the power of a becomes t to negative a. I'm just doing that here to aid clarity for you when we continue with the solution and start to equate the indices. With problem 2, solution continued, just repeated the top line for reference. So now we're going to equate the indices, first of all for length. So on the left hand side of our equation we have L to the power of 2, so 2 on the left hand side. Again, scanning the right hand side for L, we have L to the negative 3, we have L to the a, so I add the a. And we have L to the power of b, it's the third law again of indices there, so I add the b. Just to simplify the equation, I add 3 to both sides, so now I have an equation of 5 is equal to a plus b. I've labelled that as equation 1 for reference. I can't solve that directly, I have two unknowns in one equation, so that cannot be solved. So I need to generate another equation, so this time I'm going to equate the indices for time. Again, on the left hand side now, I have t to the negative 2, so there's my negative 2. On the right hand side, scanning for dimension t, I have t to the negative a, so negative a on the right hand side. That's the only t dimension on the right hand side. Now we have the value of a, we can see that a is equal to 2. And from equation 1 above, I simply transpose the equation. I've subtracted a from both sides of the equation, so b is equal to 5 minus the a. And from above I know that a is equal to 2, so that becomes 5 minus 2. So the value of b is 3. Just note for your reference, I could have equated the indices related to the time dimension first of all, which might have been preferable in this particular problem, as I would have solved directly for the exponent a. So just note you can apply the equated indices for any dimension in any order. So we can write now the final equation for work. Work is equal to a function of rho, velocity to the power of 2, and the height to the power of 3. So that's the solution for problem 2. Here's problem 3. The rotating force, capital F, applied to an aircraft propeller was found to be related by the formula F is equal to mv to the power k divided by r, where m is the propeller mass in kilograms, v is the linear velocity in meters per second, and r is the blade radius of gyration, meters. So using dimensional analysis and assuming dimensional homogeneity, we've got to find the value of the exponent k associated with the linear velocity in the above equation. I haven't stated the answer on this particular problem, but I would encourage you to stop the presentation and attempt problem 3 here, and I will show you the full work solution on the following slides. So here's problem 3, solution. So we're given the formula F is equal to mv to the power k divided by r. So let's initially consider the units and the dimensions of each of the quantities above. So force F is in newtons. Don't forget that's a name given to the derived SI unit. In base units, the newton is the kilogram meter per second squared, or kilogram meter second to negative 2. So that has dimensions of mLt to negative 2. The mass, lowercase m here, base unit the kilogram, in dimensions that's capital M. The linear velocity v, base unit meter per second, or meter second to negative 1, dimensions lt negative 1, and finally the radius, capital R, SI unit of the meter, so dimension is L. So we can now write the above formula for F in terms of the dimensions. On the left hand side we have the MLT negative 2 for the force. Then we have the mass, capital M, the velocity, LT negative 1, raised to the power K of course, trying to find the K. That's all divided by the radius, dimension L. Problems 3, solution continued. Just repeated this top line here from the previous slide. On the next line, I just use the indices reciprocal rule here. So instead of dividing by the length, I effectively bring it to the top line, and I multiply L to the negative 1. On the next line, I simply divided both sides by M, so M cancels here, here. So that leaves us with now LT negative 2 on the left hand side, and the LT negative 1 to the power K, multiplied by L negative 1 on the right hand side. So that was dividing throughout by M. On the next line I simply multiplied throughout by L. So on the left hand side I have L squared, on the right hand side the L to negative 1 disappears. L to negative 1 multiplied by L to the 1 becomes L to the 0 or unity. That's essentially applying the first law of indices. So that leaves us with the velocity dimensions on the right hand side. And notice I've also used the third law of indices here. So LT to negative 1 all raised to the power K can be written as L to the power K multiplied by T to the negative K. I don't really need to apply that step here, but I'm just trying to show it for clarity when I equate my indices. So next line I equate the indice for length, L. So on the left hand side I have L squared, L to the 2, so 2 on the left hand side. On the right hand side I have L to the K, so that's K on the right hand side. We can clearly see that K is equal to 2, so I've solved the problem. I was asked to determine the exponent K, it's 2. And just note it could be checked by equating the indice for time, capital T. So in the above formula here, on the left hand side I have negative 2 for T on the left hand side, and here negative K, and negative K on the right hand side. So again we can clearly see that K is equal to 2. So we've checked the above value. So we can now write our formula for force. Force can be written as mv squared divided by r, or of course the force can be written as mv squared multiplied by r to the negative 1, whichever solution you prefer. So that's the complete solution for problem 3. Finally, here's problem 4. The pressure head, H, in meters of water related to the flow in a pipe is given by H is equal to 0.03 multiplied by L multiplied by V to the power of X divided by 2 multiplied by D to the Y multiplied by G. And we're informed that L is the pipe length, meters, V is the fluid velocity, linear velocity in meters per second, lowercase d is the pipe diameter and in meters, and lowercase g is the gravitational acceleration, meters per second squared. Using dimensional analysis, we're asked to calculate the exponents x and y, and then state the equation. Answer shown in the bracket. So I'd encourage you to start the presentation, attempt problem 4, but again the full work solution is going to be shown on the following slides. So problem 4, solution. I'm going to let you review this at your own pace. Again, I start the problem by considering the units and the dimensions of all the quantities, the 5 quantities stated here. So problem 4, solution continued. Just repeated the table on the left hand side here for convenience. So let's apply the dimensions to the formula given. On the left hand side we have height h, we know the dimension is L. On the right hand side we have length L, that will have dimension L. We have velocity v to the x, so v is lt negative 1, of course raised to the power of x. In the denominator we have the diameter, the power of y, so that will be dimension L raised to the power y. And also in the denominator we have gravitational acceleration g, dimensions LT negative 2. Just note on the next line I've divided throughout by L. So on the left hand side I now have 1 because L divided by L is 1, and on the right hand side the L on the top line here cancel with an L on the bottom line, so I basically end up with my velocity raised to the power of x divided by e raised to the power of y. That's multiplied by gravitational acceleration. Just note for reference that 1 in dimensions can be written as mlt to the 0, anything to the power 0 is unity. And on the right hand side I simply brought the denominator terms to the top line. So note the index has changed from y here to negative y here. The lt to negative 2 in the bracket is always the power of negative 1. That's just using the reciprocal rule of indices. The next line I've simply used the third law of indices to write m to the 0, l to the 0, t to the 0, still 1 of course. And on the right hand side again I've used the third law of indices, so I write now l to the x, t to the negative x, still got my l to the negative y here. Then applying the third law to the final bracket I have l to the negative 1, t to the positive 2. And applying the third law there, that's negative 2 multiplied by negative 1, positive 2. So now I can equate the indices, first of all for time here, capital T. On the left hand side I have t to the 0, so there's my 0 on the left hand side. On the right hand side I have t to the negative x, so negative x, and t to the positive 2, my positive 2. One unknown in one equation I can solve by rearranging, so add an x to both sides. I can clearly see x is positive 2. If we again equate indices, but this time now for length, capital L dimension, left hand side again 0, here. On the right hand side I have L to the power of x, so it's my x here. Also have L to the power of negative y here, so there's my negative y. And we have L to the negative 1 here. But of course from the above line we know that x is equal to 2, so I can replace the x with 2. So 2 take away 1 is 1. So I have 1 minus the y. So rearranging we can clearly see y is equal to 1. So I've solved for my unknown exponents. And now I can write the equation for height h, the fluid, is equal to 0.03 multiplied by L multiplied by v squared, and that's divided by 2 multiplied by d to the power of 1 multiplied by g. But of course we don't usually write the powers of 1, we assume that, so I've just simply rewritten the formula again, but this time just using d. So h is equal to 0.03 lv squared divided by 2dg. And there's the solution to problem 4. So I hope this presentation has been of use to you, and as always, thank you for viewing.